Alright, so this will be our last video for chapter 3. So these are going to be some problems involving distance and intersection. Mostly the intersection problem is mostly dealing with intersections of planes, or the intersection of a line with a plane. We've discussed intersections of lines in a previous video. So moving right in, here's our first problem. We've gone over how to find the distance from a point to a line when we discussed lines a few videos back. What about finding the distance from a point to a plane? So what we do here, let's sketch out sort of a schematic. So we draw sort of a very generic looking plane, something like this, and we've got a point Q, which is probably not on the plane, or else this question is not very interesting. So Q is a point not on the plane, and we want to find the shortest distance from that point to the plane, right? So we want this distance here. We want to kind of move in a direction perpendicular to the plane and find this point P on the plane which is closest to Q. Now, by the way, we don't actually have to find that point, but it might come in handy if we do. So let's think about how to set this up. Here is a point P naught, okay, some reference point on the plane. Now we don't have a reference point, so that's actually the first thing we need to do. The first thing we need to do is find a reference point, right? And unless you get almost impossibly lucky, your reference point is not going to be the point that you're looking for. The chances are almost zero that you guess the closest point. So remember, the way you find a point of reference is set two of your three variables equal to 0, solve for the remaining variable. Looking at the equation that we have here, 3x minus y plus 4z, I would probably choose to set x and z equal to 0 simply so that I can write down a point with integer coordinates, right? Because if I set, say, y and z equal to 0, I'm going to get x equal to a third, and maybe I want to avoid the fractions. So I'm going to say if I put x equals 0 and z equals 0 in the equation of my plane, well, that's going to give me y equals minus 1. So that means that this point P naught that we have here, P naught, we can take to be 0, minus 1, 0. Okay? Q, we're given the point Q. 2, 1, minus 3. That one is given to us. All right. So now we've got to bring some vectors into the picture, and there are two vectors that we're going to construct. One we can see right away. We can construct this guy, right? Let's call that W. So W is just going to be the vector from P naught to Q, okay? And so that's going to be, well, 2 minus 0, 2, 1 subtract minus 1 gives me 1 plus 1, that's 2, 3 minus 0, or minus 3 minus 0, 2, 2 minus 3, okay? We've got that vector. The other vector that we want is the normal vector. Remember, for the normal vector, we discussed this in the previous video, you can read off the normal vector by simply looking at the coefficients in the equation of the plane. So the normal vector is going to have the 3, the minus 1, and the 4 as the coefficients of the normal vector, right? So those three values give me the components of the normal vector. So our normal vector is given by 3, minus 1, 4. Okay? All right. So what do we do with that normal vector? Well, one thing you can do is you can kind of set up. It's sometimes hard to see. When you're doing it with the plane, it's sometimes hard to see. So we could put the normal vector here as well, and we could think about, if I take this vector W, now you can kind of see that I can split it up into two pieces. I can split W up into, and let's write them in another color. Let's put them in green. This piece here and this piece here. Okay? So let me call those U1 and U2. Things are getting a little bit cluttered here. But so these two vectors, U1 and U2, what can I say about those two vectors? Well, I know that U1 plus U2 Um, they add up to give me W. I know that this guy here is going to be parallel to the plane. I know that this guy is going to be perpendicular to the plane. Well, if it's perpendicular to the plane, that means that it's parallel to the normal vector. And you can probably guess what this has to be. If it's going to be parallel to the normal vector, and it's probably easier to kind of see it if you draw it over here, right? If you draw that U2 over here and think about dropping this perpendicular, right? U2 is just the projection of W onto the normal. So we can calculate that guy. U2 is the projection of W onto the normal vector. So W dot N over N dot N times N. Okay, so this is going to give me, it's going to give me what? It's going to give me, so W dot N, we've got them here, we can, so it's going to be, so how do we do W dot N? 2 times 3, 6, 2 times minus 1, minus 2, minus 3, minus 4. So I'm going to get 6 minus 2 minus 12 over N dot N. So 3 squared, 9, plus 1 squared, 1, plus 4 squared, 16. Okay, so I get that. So I'm going to get, this is minus 14 plus 6, so minus 8 over 26 times the normal vector. Okay, now in this problem, notice that we weren't asked to find the point P, and in fact we don't have to bother finding the point P, even though that's the closest point, and we could go ahead and find it. What is the distance? Let me put the distance up top. Okay, so the distance, even though we don't know what the point P is, we know what the distance is because the distance has to be the magnitude of this projection we just calculated. D has to be the magnitude of this vector U2. Okay, so that's got to be 8 over 26 times the magnitude of N, right? I dropped that minus. I remember when you're calculating magnitudes should be positive. So if you have a negative scalar out front, you drop that minus sign. And by the way, 8 over 26, I could simplify that to 4 over 13. And the magnitude of N, actually, you know what? Let's not simplify because I know what the magnitude of N is going to come out to be. 8 over 26 times, so the magnitude of N, right? Well, remember that this guy down here, this is the magnitude of N squared. It's N dot N. So the magnitude of N is just going to be root 26. Okay, and so I could write this if I want. I could leave it as 8. I could do 4 root 26 over 13, or I could simply write that as 8 divided by root 26. Okay, so that allows us to calculate the distance from a point to a plane. You simply compute the projection onto the normal vector, and then you find the magnitude of that projection. All right, next up, intersection of a line and plane. So the scenario you have here is you've got a plane, you've got a line, right, and this line comes along, right? It's not necessarily perpendicular to the plane. That doesn't matter as long as it's not parallel to the plane. It's going to intersect at some point. So there's going to be a point here of intersection, x, y, z. Okay. So what can I say about that point of intersection? So if it's an intersection, it's on both the line and the plane, right? So the fact that x, y, z is on the line means that x has to be, let's look at this guys here, 2 plus 1 times t. X must be 2 plus t. Y must be 0 plus minus 2 times t. Y must be minus 2t. Okay? Z has to be minus 1. Oops. Z has to be minus 1 plus 3t. Okay? Minus 1 plus 3t. Right? That's what it means for the point to be on the line. What does it mean to say that the point is on the plane? Well, that means that x plus 2y minus 4z has to equal 8. So now we combine these two pieces of information. On the one hand, x plus 2y minus 4z is equal to 8. On the other hand, x must be 2 plus t, y must be minus 2t, z must be 1 minus 3t. So you can probably see where this should go. This value for x should go in here. This value for y should go in here. This value for z, it should go in there, right? That's how we describe x, y, and z given the fact that we're on the line. And so what we get is 2 plus t plus 2 times minus 2t, okay, minus 4 times minus 1 plus 3t has to equal 8. So now we clean up both sides. We've got 2 plus t minus 4t plus 4 minus 12t is equal to 8. So let's collect up all the t's on the left. We've got minus 16, we've got minus 15t, right? That's all the t terms. And let's subtract the 4 and the 2 over to the other side, and we've got 2, right? So this tells me that t must be minus 2 over 15. Okay, good. So I got a t value, right? But the t value is not what I was asked to find. What was I asked to find? I was asked to find the point of intersection. So what is the point of intersection? Well, we put this back into the equation of our line. And we get that, so x is 2 minus 2 over 15. Okay, so that's 28 over 15. All right, 2 is 30 over 15. Y is going to be equal to minus 2 times t, so y is 4 over 15. And z is equal to minus 1 plus 3 times minus 2 over 15. So that's going to be what? That's minus 2 over 5, and then I'm subtracting another 5 over 5. Minus 7 over 5 if we simplify the z coordinate. Okay, so that point of intersection that we want, it's going to be the point 28 over 15, 4 over 15, and minus 7 over 5. Okay, and if you want to make sure that you didn't make any mistakes along the way, one of the things you could always do is you could take those 3 points, you could plug them back into the equation of the plane and make sure that those actually add up to give you 8, which they should. I'm going to skip that verification so that we can move on to another problem, but that's something that you should check. Make sure I didn't make any mistakes. It's possible I made mistakes. You know, there's a lot of numbers floating around here. So double check. Let me know. If I messed up, we can always issue a correction. All right, on to the next problem. Describe the intersection of planes. So this one is a bit trickier. There's a few ways to do it, but if you think about what this means, what do they look like geometrically? What do these planes look like? Okay, so I've got one plane, kind of draw it here like this. Okay, and there's another plane which is going to kind of come along and it's going to, I don't know, cut through that plane. All right, so there's some sort of intersection between the two planes. So where they meet is, well, they intersect along a line. So there's some line of intersection where those two planes meet. Okay, all right. So we expect that the intersection between two planes, it should look like a line, right? And the line is expected. How do you describe this line? Okay, so let's suppose that let's suppose I have x, y, z, and it's on the line of intersection. Okay, well that means that 2x minus y plus 4z equals 2, and at the same time x plus 2y minus z has to equal 5. There are a couple of ways of tackling this problem. The best method for tackling this problem is one that we won't really encounter until we kind of learn how to solve systems of equations. In fact, I think we're going to probably leave most of this solution for a while. There are a couple of approaches that you could take. One approach that you could take to this problem, if you really wanted to do it now, is to say, well, here's a point in that line of intersection. I could do the normal vector for the first plane, normal 1. I could find the normal vector for the second plane, normal 2. And once I had those guys, I could use that. So then I said, well, that line is parallel to both planes. Parallel to both planes means perpendicular to both normal vectors. So one of the ways I could do this is I could say, well, this v must be the cross product of the normal vectors. Normal 1 crossed with normal 2. Okay. Fine. So normal 1 crossed with normal 2, that works. How do I actually find a point, right? That gives me the direction vector. How do I find a point? Finding a point. Well, we might try to say, let's say we find a point where z is equal to 0. Okay? Can we find a point where z equals 0 that's common to both planes? Well, then I would have to have 2x minus y equals 2, and I would have to have x plus 2y equals 5. Okay? And so then maybe this one I could say y equals, move the y over, y is equal to 2x minus 2. And so then x plus 2 times 2x minus 2 is equal to 5. So 5x minus 4 is equal to 5. X is equal to 9 over 4. Y then would be equal to, so 2 times 9 over 4 would give me 9 over 2 minus 2, which gives me 5 over 2. So I could do this. I could find a point. So I could find my point. P naught is going to be 9 over 4, 5 over 2, and 0. And then I could get my direction vector. So I could calculate. I'm gonna skip this. If you want to compute it, you can. I could calculate v is the normal vector, normal 1 cross normal 2, and I could figure out what that is. And then we know, well, once you've got a point and a direction vector, you know how to write down the equation of that line, right? So now that's one way to do it. You can write down the equation of the line that way. Later on, we'll see that the right way to actually solve this problem is not by this method. The right way to solve this is to say, well, look, that point of intersection, it's got to be a solution to both of these equations, the simultaneous solution to both equations. And so you want to think of this as a system of two equations with three unknowns, three variables. Okay, and we'll develop techniques for writing down the general solution to that system, and when we do that, we'll see that that solution does indeed resemble the equation of a line. Okay, but we're a little ways off from that. That's a kind of something for the future. So this is the sort of problem that I wouldn't ask you to solve yet. In principle, it can be done, but we might as well wait until we develop better techniques. Okay. Here's just a quick one, just for fun. People like to have formulas for the distance, right? So remember, we did this before. We said, all right, if I've got a line, okay, so here's my line L, and I've got a point P naught on the line. I've got a point P which is not on the line, and I want to find this distance here. So I want to find that distance. So, okay, so let's say the direction vector, all right, so we've written D for the direction vector. Here's my direction vector, D. Actually, let me redraw this. Let me draw it. I'll draw it a little bit longer. It doesn't have to be, but it'll make it kind of easier to see what's happening. So I draw this direction vector D, and while I'm at it, let's put in this vector here. So we'll say V. So V is this vector from P0 to P. All right. So what can we do with this? Well, let's see if you remember your cross product stuff. I can form a little parallelogram here, right? I can form a parallelogram like so. Okay. Here's the distance we're looking for. Then is the height of the parallelogram. Okay. Here's the base of the parallelogram. So one of the formulas that you learn for the area of a parallelogram is the area of a parallelogram is just base times height. Okay, so that's equal to, so the length of the base is the magnitude of this vector d. What is the height? Well, if I know this angle theta, the height, that's the opposite side. So the height is given by, well, the hypotenuse is the magnitude of v, and I should be doing sine theta because I'm on the opposite side. But I know what that is. That is simply the magnitude of the cross product. This is the magnitude of the cross product, v cross d. Okay, well, we've got it now, right? Because I know this already. I know that this is the area of the cross product. We've gone over that. That's the area of the cross product. And what do I want here? I want h. I want to solve for h. H is that distance. So h is, well, the area over the length of the base. So it's simply the magnitude of the cross product over the magnitude of d, which is that formula we're looking for. Okay. So you've got a formula. I don't recommend using this formula. I mean, for one thing, you'd have to memorize it. It's going to take up space in your brain that you need for other things. The other thing is, maybe you're given one of these distance problems where you're also asked to find that closest point. This formula doesn't give you any help with that. It simply gives you the distance, right? It's kind of a roundabout way of finding that distance. So it's an interesting little fact, but it's not particularly useful in practice. All right. Distance between parallel planes. Here's one that's a little bit more of a challenge, but it's still not too bad. The key to doing distance between parallel planes is to realize that there's really nothing different here than when you're trying to find the distance between a point in a plane. So the idea is on the first plane, okay, you choose a point P0 on the plane. And the second point, you get a reference point Q0 on the second plane, right? And so the distance between the planes, that's just going to be the same as the distance between any point on the second plane and the first plane. Okay. So if we can find one point on either plane, we can construct this vector, and then we can just do like we did on the very first example and project onto the normal vector. Okay, so we find points. Okay, on the first plane, I'm going to take P0 to be, well, here's one that just jumps out at me, 0, 0, 2. All right, if I put x equal to 0 and y equal to 0, I'm left with simply z equal to 2. On the second plane, well, why not? 0, 0, 7. Okay, that's going to give me a particularly simple vector. So now I'm going to form the vector v, the vector from P0 to Q0. And, well, this guy's easy. 0, 0, 5. Okay. So then we read off the normal vector n, which is given by 2 minus 3, 1, and we calculate the so the distance the distance is going to be the length of the projection of V onto N. Okay, so let's kind of calculate things quickly. Let's do it up here. V dot N, well that's 5, right? 0 times 2, 0 times minus 3, 5 times 1. N dot N, we've got 4 plus 9 plus 1, that's 14. All right, 2 squared minus 3 squared, 1 squared. So this is the length of 5 over 14 times N. So that's 5 over 14 times the length of N, which is 5 over 14 times root 14. Leave it like that if you want, or write it as 5 over the square root of 14. And you're done. You've got the distance between parallel planes. Okay. The last one we'll set up, and I'm not going to go all the way through this one because it's gonna take too long. Find the distance between skew lines. This is a trickier one. This is kind of, if you can do this problem, you can do pretty much anything that we could throw at you. So here's how you think about this skew lines, right? You've got one line is kind of up here, and another line is down here. And they don't intersect. They're not parallel, but they don't intersect. And one way to think about why they don't intersect is that these two lines, they lie in parallel planes, right? One line in one plane, one line in the other plane. They don't intersect. Now, the distance, the first part is easy. The distance between the two lines, well, you've got points on you choose points on the two lines. Let me redraw it, right? Those points aren't probably kind of sitting quite so close together. Maybe this one's over here, okay? P naught, Q naught, something like this, right? And you've got direction vectors. You've got a direction vector V. You've got a direction vector W. So where is that information here? Here's P naught. Here's V. Here's Q naught. Here's W. And so those two vectors, they lie in parallel planes. And so these lines are they're in parallel planes. And we know what the normal vector is. The normal vector is simply the cross product. Okay? So once you realize that this is going on, then finding the distance between skew lines, if all you want is the distance, you go back to this example here. It's exactly the same, right? Distance between skew lines has now become distance between parallel planes. Once we do that cross product, we've got the normal vector. We've got one point on either plane. We've got our P naught. We've got our Q naught. We form the vector same as, so we do Q naught minus P naught, same as here, right? So we would take the vector from here to there. We form that vector, and we find the normal vector. And aside from having to do that cross product to compute the normal vector, we proceed as in the previous example. It's exactly the same as in the previous example. Now, suppose you wanted to find those points that are closest together, finding the closest points. Right. So then this becomes the same. So let's just kind of point that out. So this becomes the same as the last example, at least as far as finding the distance. What about finding those points? So you know that the point has to be on both planes. So this gets really, here's where it comes in. Okay, so you're going to take a point P. So P is going to be on the first line. So it's going to look like 3 plus 2s s 1 minus 3s, right? Using so it's the 3 plus 2s 0 plus 1s using the vector equations. All right, 1 point on one plane, 1 point on the other plane. Q, so Q has got to be, so Q is going to be 1 plus t, and then 1, and then minus 1 plus t, right? So then you form this vector PQ. And so PQ, we do head minus tail, is going to be t minus 2s minus 2, 1 minus s, and then t plus 3s minus 2. Okay, and so this is kind of, so this P and Q here, the P and Q that you found, what are these guys? They are the closest points. P, Q. Okay, so P and Q are closest if PQ is parallel to the normal vector, right? So how do I guarantee that this thing is parallel to the normal vector? Well, if it's parallel to the normal vector, it's orthogonal to both v and w. So I would need v dot pq equal to 0. I would need w dot pq equal to 0. And these would give me two equations in my two unknowns, s and t, and I could solve for s, I could solve for t from those two equations. So you'd end up with sort of two equations in two unknowns. You solve for s and t. Then you put the s value back into the first equation to find p. You would put the t value back into the second equation to find q. And then you'd be able to verify that the distance between those 2 points agreed with the distance that you found using the parallel plane method. But we'd be looking at another 5 to 10 minutes of work to come up with those, and I don't want to make the video that long. So I think we'll leave this one out, and if you really want to see an example, there's one written up in the textbook, and you can take a look at it there. Okay, so that is it for chapter 3, and we'll continue after the test with some videos starting with the chapter 4 material.